Grade 12 pre-cal, lesson 7.1/7.2. It's quite a long lesson. There's like 10 pages, I think, in this one, so bear with me on this one. So let's start with part one, solving trigonometric equations over a given interval. So what we have here is we're going to solve for theta. And theta is between 0 and 360 degrees. Okay, so if you, this was from grade 11. So what we do is we rearrange this and try to solve for theta. You got to get theta by itself. So, right, you move the 2 over to the other side, then you divide everything by 3. Okay, so we end up with sine theta equals 2/3. So the first thing you do is you look at, hey, sine is positive here. So where is sine positive? Well, it's in quadrant 1 and quadrant 2. Okay, so that's our two answers that we're going to look for. Well, then how do we find it? Well, you do theta r, do the inverse sine of it, and you get 41.8. So what that means is theta, the distance between the initial and the end piece here, right, the terminal arm is 41.8. The distance between 180 and this one here is 41.8. So how do we find the two of them? Well, if it's in quadrant 1, it's easy. It's just whatever it is, theta 1 is 41.8. If it's in quadrant 2, then it's 180 minus 41.8, or 138.2 right there, right? And those are the two there. So flip to the next one. We'll do another example here. So example 2, given the tan squared theta equals 1, what are the solutions on the interval? Oh, now careful. This is now between 0 and 2 pi. So we're in radians, right? And remember, 1 full lap is 2 pi. Okay, so we do the same thing again. Tan squared theta equals 1. We take the square root of it. And you got to remember, take the square root, it's plus or minus 1 there. So tan is sine over cosine. So what we can do is we're looking for tan equal to 1. If you know on the unit circle, you remember that tan equals 1 at certain spots, and it's the 45s is what you're talking about here, right? So for tan being positive, right, that's in quadrant 1, that's in quadrant 3. For tan being negative, that's in quadrant 2, and that's in quadrant 4. So there's actually 4 answers in this case, and our answers in radians, because originally up here it says between 0 and 2 pi. But the pattern is still the same. Okay, example number 3. The exact solutions between 0 and 2 pi. Again, we're in radians. For cos squared theta plus cos theta equals 0. So this one, we have a common factor, and the common factor in this case is cos theta. So we pull that out, and we end up with cos theta equals 0, and then this cos theta plus 1 equals 0, and we rearrange it. So cos is 0. Where is cosine 0? Well, now, if you remember, this is in radians, so don't do it in degrees. You can think of degrees if you want, and then change it back with 90 and 270. Whereas cos negative 1, well, that's just pi. That's basically the 180. So our final answer is all 3 of those together. So again, break it down into its pieces, and then use your unit circle and figure out where the answers are going to be. Example number 4. Okay, so find the solutions of 2 sine theta minus 3 sine theta minus 2 equals 0. So some people still have trouble factoring these. If you need to, convert the sines to x's, and then you got a polynomial, a trinomial up here, factor it, and then put it back in its normal form. And they want this between 0 and 360, so we're dealing with degrees again. So this one factors down into 2 sine theta plus 1 and sine theta minus 2. And they both equal 0. Split them, right? Set them equal to 0 and do all the math, right? Move the 1, divide by 2. This one just move the 2. So sine theta equals a half. Just look at your unit circle, and you can see that it's theta equals 210 and 330. Now, what about this one here? Sine theta equals 2. Well, you realize there's no solution, right? Sine and cosine can't be greater than 1 or less than negative 1. Tans can be, right, because of the ratio, but sine and cosine cannot. So in this case, there's no solution for that one. Okay, so now those are all exact solutions. Part 2 of this one is creating a general solution. And what a general solution is an unlimited number of answers. So what we do is we create a real number solution. Okay, so let's look at this first one. So find all real number solutions for sine theta equals 0. Okay, so that would be, and we're in radians. So theta would be like 0, pi, 2 pi, 3 pi, 4 pi. You're basically going a half circle around each time. You're going half laps, right? So the answers are half laps apart. You would start at 0, right? Go to pi, and then 2 pi, and then 3 pi, and then 4 pi. And it goes on indefinitely. So what we can do is we can create a general solution for that. So one of them is 0 plus k pi. And k pi is just an integer. That's why we put this k has to be an element of I, which means it has to be an integer. It means no decimals, no fractions, anything like that, but it could be positive or negative. Or if you wanted to shorten it up, it could just be k pi, where k is an integer. Now let's just double check this. So if k was 0, 0 times pi is 0. Yeah, that would be our starting point right there. What if k was 1? Then it'd be 1 times pi, so that would be just pi, which is, yeah, halfway around. Perfect. What if k was 2? Yeah, 2 pi, so that would be all the way around, 3 pi, right, and then 4 pi. So this little general solution down here gives us the same answers as all our thetas up here. Just an easier way to write it. Okay, let's look at another example. Example 2, cosine theta equals -1 over a set of real numbers. So in this one, we want cosine is -1. So -1 is right over here at pi. But the next solution wouldn't be back over here at 2 pi because that's positive. So it's you start at pi and then you go all the way around. And all the way around, one lap is 2 pi, right? So it'd be pi, and then 3 pi, and then 5 pi, and then 7 pi. Okay, that's good. You can write all those numbers down, but let's create a general solution. So in this case, it's 2k pi, right? So it's pi. We start at pi. That's our first point. We start at pi, which is over here, and then we go around 2k pi. So that's basically a full lap around, a full lap around, a full lap around. So let's double check that this works. So if k was 0, then all of this would be 0. Yep, we start at pi. Pi times 0 is 0. We start at pi. If k was 1, it'd be 2 pi. So we start at pi, and then we go all the way around 2 pi. Yeah, it works every time. So you have to think about laps on this one. So we start at pi, and we do a full lap, which is 2 pi every time. Okay, example number 3. Solve for theta where the domain is a set of all real numbers. Now, if you look at this one, sine theta equals √3/2. And what you can do is you can look at your unit circle. You can find that √3/2, because sine is positive, occurs in quadrant 1 and quadrant 2. And it's pi/3 and 2 pi/3. Now, but the problem is if you look at the distance between those two, that's not a full lap. That's not even part of a lap. Okay, so what we do is we have to split this into 2. So let's look at the first one. The first one starts at pi/3. And then to get all the way around would be 1 full lap to get all the way around again. So that's why we do 2k pi, where k is an integer. Okay, and then we separate and we go to 2 pi/3. So 2 pi/3, and to get all the way around again is another full lap, which is 2 pi. So in this case, because of the distance between them, it's not perfect laps. We have to separate them into pieces. So pi/3 plus a full lap around, and then 2 pi/3 plus a full lap around. And you write it like this with the k is an element of I all the time. Okay, example number 4. 4 sine squared theta -1 equals 0. Again, do all the work, rearrange it. So move the 1, divide by 4, take the square root. So we end up with plus or minus a half. So there's technically 4 possibilities, right? So pi/6, 5 pi/6, 7 pi/6, 11 pi/6. And just look at your unit circle and you can see that where sine is positive or negative a half. Okay, so let's start with the first one. So pi/6 works here. But in this case, we don't have to go all the way around as a full lap. We can go a half lap. So pi/6 and a half lap would take it to 7 pi/6. Another half lap would take us to pi/6 again, and then it just keeps working around. So we can split this one into 2 also. So pi/6 plus k pi. So k pi, whatever k is, so 0, 1, 2, 3, or 4. So pi/6, and if this k was a 0, right, it doesn't move. If k was 1, it would move to 7 pi/6, and then so forth. And then we can look at the 5 pi/6 and do the same thing. It starts at 5 pi/6, and it goes half lap around, half lap around, half lap around. And what that does is it gives us a solution that shows us all the possibilities. So in this one, pi/6 plus k pi and 5 pi/6 plus k pi. So they're getting a little more complex, but it's still the same pattern over and over again. And the only way to really do this is practice, practice, practice. Okay, let's look at example 5. Now, find all solutions in radians for tan x equals 2. Whoa, well, tan x equals 2 doesn't exist on our unit circle, right? We can't just see it. So what we got to do is we got to use the old calculator to do this one. Now, this is the first time you're actually going to change your calculator to radians. So instead of degrees, change your calculator to radians. Where is tan positive? Tan is positive. We know this in quadrant 1 and quadrant 3, right? So we do tan in inverse tan to -1 or inverse tan of 2. We end up at approximately 1.11. So think about this. So that distance right there is 1.1 radius. And that actually makes sense because 0, right? Pi is 3.14. So 90 degrees or pi/2 has to be half of that at 1.57, right? So 1.1 appears in quadrant 1. You can see it right there. And we also have to do this one over here. So it's 3.14 plus 1.11 or 4.25, right? And we can just keep working through that. It's an unlimited number here. So to do that as a solution here, we do 1.1. That's where we start. And we do half laps around, right? Half laps, which is, again, k pi, right? So 1 pi, 2 pi, 3 pi, 4 pi. Half laps around for each one. Okay, last example. Example number 6 here. Okay, so this one here you got to look at this. And it says find all real solutions for sine of 2x. Well, the problem is that 2x in there is kind of difficult to work with. We know what root of 2 over 2 is, right? That's the 45s or the pi over 4s when we're dealing with this. So in the end, what we do is we can do all the work, and in the end, divide everything by 2, and that'll help us with it. Okay, so let's take a look at this. So we end up with 2x equals 5 pi over 4, right? 5 pi over 4 is just root of 2 over 2. And the other one is 2x equals 7 pi over 4, right? Those are our two answers in this case because we're dealing with sine. Okay, so what do? Well, let's create a general solution. Where are those ones? So 2x equals 5 pi over 4 plus 2k pi. So 5 pi over 4 here, all the way around, right, which is one full lap, which is 2 pi, or 2k pi in this case. And the other one is 7 pi over 4, all the way around is 2k pi. So there's our general right there. We've created the general. Now, what did we say at the top here? Hang on, look, back up here, right? We divide everything by 2, right? Right, the negative root of 2 over 2 gave us the negative signs, right? Quadrant 3, quadrant 4. But what we have to do is we got to divide everything by 2. So now divide everything by 2. Well, that's easy. 2x divided by 2 is just x. 5 pi over 4 is just 5 pi over 8. That's easy. 2k pi divided by 2 is k pi. Oh, well, actually, that's not that bad at all. So what we do is, if you think about this, treat it like you normally would. Ignore the 2 for in the meantime, right? Do all the work, figure out what the general solution is, and then divide by 2. Now, how would that work if it was a 3 up here? Work exactly the same way, but at the end, you would divide everything by 3. So down here, we would have our general solution right there because we divided everything by 2. Okay, give those questions some work there, okay?